Webinar presented by Delubal Software. Today we'll be working in our structural analysis and design software RFEM 6. The topic for today's presentation is AISC Design Guide 26 Blast Analysis in RFEM 6. My name is Amy Heilig. I'll be your presenter. I'm the CEO of the US office, and I'm also a sales engineer, and I'm located in Philadelphia, Pennsylvania. My colleagues Alex Baca and Siska Cho will be your moderators, answering any questions you may have. They're both support engineers, also located in our Philadelphia office. We always want to encourage everyone to ask questions throughout the presentation. You can do so within the GoToWebinar dialog box as shown here. If by chance we don't get to all your questions, we'll certainly send you a follow-up email afterwards. So we'll quickly go through the content that we will cover over the next hour today. And we want to begin with the blast loading concept and the application for a time history analysis. We will be referencing the AISC Design Guide 26 and move into our example that you see over here on the right-hand side, applying the design guide directly within RFEM itself. We'll talk about the loading and the time diagram input. We will carry out a linear time history analysis to begin. And at the second part of our example, we will carry out a nonlinear time history analysis. So we have recently released this solver within the time history analysis add-on in RFEM 6. Just a quick note about this is a phased release. So not all capabilities are quite there yet. We'll talk a little bit more as we get into that within the example today. And of course, through these examples, we will take a look at the structure, response, and results. This PowerPoint presentation is available as a handout in the GoToWebinar. The model can also be downloaded directly on the registration webpage that you registered for this GoToWebinar if you also wanted to follow along with today's example. So we'll turn now to the blast loading basics. And the design resources that we'll be referencing today is, of course, the AISC Design Guide 26. So this is the design of blast-resistant structures. Now, the United Facilities Criteria, UFC document 3-340-02, will also be what we reference today as one of our resources. Now, there are many other references, literature out there for a blast analysis, but again, for our approaches and example today, we'll be utilizing these two. So let's talk a little bit more about factors that are going to influence the structural damage when we talk about these rare blast loading. So the structure materials, the mass, the stiffness are all certainly going to influence this. But we also want to take a look at the explosive type. How close is the distance to the structure? Obviously, if the explosion is closer, we're going to see more localized and global structural damage than if the explosion is further away. The building geometry will also play an influence. And then the blast orientation to the structure. So elements facing the blast will see higher loads and more damage than what we see of the elements that are parallel to the blast. And finally, the surrounding structures or adjacent elements. These can also affect blast patterns. We could see load amplification or load reduction. And the ultimate design goals with something like a blast analysis is to avoid loss of life. It's not necessarily to avoid extensive structural damage. This is sometimes inevitable, but how can we prevent progressive collapse and ensure that the structure is sufficiently redundant? So we often see steel used as a primary structural system for blast loads, and this is due to the large inelastic deformation capability without the loss of load carrying ability. So we're talking about the plastic deformation here that steel allows for, therefore it has a very high ductility and flexibility. In contrast, concrete certainly has a higher mass and stiffness to resist these high impact loads, also a higher temperature resistance, but it's a very brittle material. So it's not going to be as ductile as what we see here with steel. So both of these materials certainly have their pros and cons. So turning now to Design Guide 26 to talk about the blast load application and this idealized pressure time history for blast load. over here on the right-hand side is taken directly from the design guide. So we want to talk about a few of these variables that go into creating this diagram itself. And we start off with the peak overpressure. So this is going to be the pressure above the ambient atmospheric pressure, hence the name overpressure. And this is an instantaneous pressure arriving at the structure. So we have this blast load taking place at time equals 0. It takes some time for the blast wave to reach the structure. So we have our time of arrival, and then we see this instantaneous rise in pressure on the structure itself. We then have the positive phase duration. So this is the time for the pressure to return back to that ambient pressure. We also have in the positive phase duration what we call the positive impulse. So this is the total pressure time energy applied during the positive duration, and this is simply the area under the curve. Now, in addition to the positive phase, we also have this negative phase duration. So this is the energy, the impulse, again, that area under the curve that follows the positive phase, where pressure actually falls below the atmospheric pressure. So this same diagram is shown over here on the right-hand side, but you'll notice we have a couple different lines here. The first is going to be the free field blast load represented by this dotted line here. And then we have the solid line that is the reflected blast load. So let's go into a little bit of the details regarding the differences between these two. We start first with the free field blast load. This is also known as the side-on blast load, where this blast actually travels parallel to a surface. It more or less sweeps over this surface with no impeding objects. So we might be talking about sidewalls, a roof, a rear wall. It's certainly not the surfaces that are oriented directly to the blast. Now, we often see the subscript SO for side-on used throughout literature to represent this particular loading. Then we have the reflected blast load. So this is where the blast load strikes at an angled surface other than parallel. So we certainly might see this for a wall that's oriented directly normal to the face of the blast load itself. And you'll notice that we have a reflected pressure piece of bar that's significantly greater than our side on. And this makes sense because it's closer to the blast and oriented normal to the face of it. We calculate piece of bar with the equation shown here. So we take the side-on pressure, the incident pressure, and we multiply by what we call the reflection coefficient C sub R. Now, we are going to reference the UFC document 3-340, in particular figure 2-193. So within this plot along the x-axis, we can see here the angle of incidence. We would determine what our angle of incidence is, follow this up, and you'll notice that the peak incident overpressure is given with these various colored lines. This is also known as the side-on pressure. We follow this over to the y-axis to get the reflection coefficient value. Now, we may be wondering, well, what is the angle of incidence along the x-axis? We'll refer to this small diagram over here on the left-hand side, where we have our initial blast wave direction. And this travels to our target element. So this might be a wall element, for example. And we're going to see this load reflecting normal to the face of the surface, hence why we see this 90 degrees here. The angle of incidence then is measured as this initial blast wave in comparison to this reflecting load. And this is ultimately what we use with figure 2-193. So turning now to Design Guide 26 assumptions here for creating these time diagrams. And we're going to begin first with the pressure time history positive phase. Well, Design Guide 26 states that we can actually simplify this to a triangular distribution, where we still have this instantaneous rise in pressure, but instead of a curved decay here, we have a linear decay back to the ambient pressure. But it's really important that we still maintain that peak pressure value and the impulse, which is the area under the curve. So therefore, we have this fictitious time here that we need to determine in order to simplify this with this triangular distribution. Well, the equation that we use for this duration is equal to 2I over P. Moving on to the pressure time history for the negative phase, we're actually going to neglect this for this demonstration. So a little bit simpler approach here, but we certainly don't want to always neglect this. For example, when we have elements that are weaker in the reverse loading direction, or if we have a structure with very short natural periods compared to the load duration, then we certainly don't want to neglect this negative phase here. But again, for example purposes for us today, we will go ahead and not take this into account. Now, there are a few other considerations listed at the bottom of the slide here that we will also not be taking into account. For example, drag forces from a dynamic pressure. These can develop just similar to like what we see with wind loads. If we have large openings for our structure, then we would want to account for interior loads due to leakage. So this blast load can actually enter in the interior of the structure, and we're likely going to see structural damage at the interior rather than only taking into consideration the exterior. Also, we talked a little bit about those adjacent objects. If we have buildings that are in front of our target structure that we're designing, this could certainly be beneficial because we would see the shielding or a load reduction. But in turn, these adjacent objects can also cause a reflection or load amplification. Again, not considered for today's example, but all very important points to consider if you are carrying out a blast analysis. So we're now going to turn to RFEM 6, and we want to begin our example today. And for those of you joining us that are not familiar with our program setup, I'll do a quick explanation here that RFEM 6 is our base program. This allows us to fully model the structure, we can load it, and we can run a full static analysis. But when we want to carry this out further with a dynamic analysis, we will need to activate the additional add-ons that are listed here. So I'll give a quick overview, including this first add-on, the modal analysis. So this calculates the structure's natural periods, the frequencies, the mode shapes. We actually are going to carry out a quick modal analysis for our structure today for damping purposes. The response spectrum analysis will generate seismic loads according to standards like the ASCE 7, the NBC. We have the pushover analysis add-on. This is an advanced seismic analysis taking into account the structure's nonlinearities. Now, we won't be touching on either of these more seismic focused add-ons for today. But finally, we do have the time history analysis, and this will certainly be a big part of our example once we do get into RFEM, where we can apply these forces to the structure and we can tell them how they should vary in magnitude over a set time period. So before we get into the program, we'll move on to our next slide here, where we're going to kind of lay out the example that we're pulling directly from Design Guide 26, example 2.1. And given in this example problem, we have a one-story steel structure. It's 50 feet in the short direction, 70 feet in the long, and 15 feet in height. I did take a simple screenshot here directly from the design guide, a nice plan view, and then we also have an elevation view. Now, in the short direction, we have braced frames, and in the long direction, we have rigid or moment frames. All of the cross sections used should be hot rolled cross sections. And then for our roof deck and our wall panel, we will set these as ribbed metal decking. And finally, we have the blast load itself. So the blast charge weight is going to be 500 pounds. And the charge distance is going to be 50 feet. So we can see this represented here, this blast load located 50 feet from the front face of the structure. Now we want to move on to our solution, and the solution is generating or calculating these time diagrams that we will eventually input into RFEM itself. And we begin with the scale distance Z. So in Design Guide 26, this states it's a simple equation here of our charge distance over the cubed root of the charge weight. We know this is 50 feet for the distance, 500 pounds for the charge weight, and we get a value of 6.3. So we're going to now refer back to the UFC 3-340, and in particular, figure 2-15. because we need to determine all of these variables from the idealized pressure curve. And this is actually done so directly within this figure itself. Now, before we get into the actual values, there are some assumptions made with this particular plot. So for example, this is assuming a hemispherical explosion, that this explosion is taking place at ground level. If you have an explosion that takes place, let's say up in the air, a spherical explosion, there are different plots that you should reference. This also assumes that our structure is at sea level. If we have any other altitude other than sea level, then there are some scaling approaches we could take directly from the UFC. And finally, this plot does assume a fully reflected surface. So if we had any angle, remember a couple slides back, we'd want to refer to that reflection coefficient, angle of incidence, to maybe scale our pressures and variables accordingly. So we've determined that z is equal to 6.3. So we simply plot it directly on this figure. And as we follow this line up, we have the various variables for the idealized pressure curve given to us here. And that's what's listed within this table. Now, you'll see here the reflected peak pressure for the positive phase, side-on peak pressure, positive. Remember, we're neglecting that negative phase entirely. So from this information, we get the value shown here within this middle column. Now, some of these variables require a step further where we need to input in our charge weight to get the final calculated value. So that's what you're seeing listed here within the third column. So let us begin with the reflected pressure for the front wall in particular. Now, remember, as we see over here on the right-hand side, following Design Guide 26, we are going to simplify the idealized pressure curve with this equivalent triangular shape. But we want to ensure that the peak pressure, P sub r, and the impulse, I sub r, these values are preserved. So if you remember a couple slides back, we don't know what this equivalent duration is, but we have a pretty simple formula for this. And we just simply input the impulse and the pressure. This information was given to us directly in figure 2-15 that we determined here on the previous slide. So we take these values, input them in, and now we get a time duration of 6.19 milliseconds. So we'll now move on to the side-on pressure. So this is going to be the time diagram for the sidewalls and the roof. Now, for simplicity and also a little bit more of a conservative approach, I am going to use the same scale distance Z at the front wall center line as what I'm using for the sidewalls and roof. Now, technically, the pressures might decrease as we move along the length of these sidewalls and roof, but again, a little bit more conservative approach here. So we have a similar triangular shape shown over on the right-hand side, but we would fully expect our pressures to be significantly lower. Our impulses will be lower as well. Again, we don't know this time duration. Well, we know P sub O and I sub O from the previous slide, figure 2-15. We input them into this equation and we are calculating here our time duration of 7.71 milliseconds. And now finally, we turn to the rear wall. So for this one, we do want to modify our charge distance. This rear wall will take into consideration the distance from the blast to the front face of the structure, which is 50 feet. But then we also have the length of the structure of 70 feet. So our new distance will add these two together to get 120 feet. Well, modifying also our scale distance with the equation r over the cubed of w, we're going to input in the 120 feet. We still have 500 pounds, and we get a value of 15.1. So we're going to use the same UFC figure 2-15 here. We're going to plot our Z value, and we're going to get the various parameters now for our rear wall presented within this table. Again, the positive phase duration, but you'll notice that I did not list any of the reflected pressures or the reflected impulses. That's because this back wall is not exposed normal to the face of the explosion itself, unlike something like the front wall. So therefore, we're more interested in those lower pressures, like the side-on peak pressure here and also side-on impulse. Now, again, for that triangular distribution, we don't know our time duration. We input in this information here, and we get a value of 19.1 milliseconds. Now, the rear wall is a little bit unique too, in the fact that we aren't going to have this instantaneous rise in pressure, like what we saw with the front wall or even the side walls and the roof. It's going to take some time for the pressure to linearly increase to the value of the peak pressure, and then we linearly decrease. So we know the time of arrival, that's equal to 66 milliseconds. And that was just given directly from figure 2-15, as you see here on the previous slide. Well, we are now looking to solve for T sub 2 here, which is the time to the peak pressure. And we account for this given in Design Guide 26 by taking the time of arrival, and we will add L1 over U, where L1 is the span of the element parallel to the traveling wave. And in our case, this is the building height of 15 feet. U is going to be the shock front velocity. This is given directly in figure 2-15. We input these values into this equation and we get a time duration of 77.9 milliseconds. So now we know T sub A, we know T sub 2. The final time we need to determine is this T sub F. So this is also a simple equation here. We're just going to take T sub 2 that we solved for above, and we're going to add in that equivalent duration that we solved for on the previous slide, taking into consideration the impulse and the pressure here. We take 19.1 seconds, we add it to 77.9, and we get our final time point here of 97 milliseconds. So now that we have the front wall, the side walls, and the roof, and the rear wall, let's summarize these all together. So you'll notice that over on the right, I have plotted this out as a diagram. So this is going to be our time diagrams for these separate elements, but yet they're all going to be acting together with this blast analysis. So on the bottom, we have our time in milliseconds. And each one of these plots represents the different areas of the structure. So we have our front wall shown in green, which we would fully expect the peak pressure here to be higher than our sidewalls, for example. In either case, for the sidewalls and the roof shown in orange, we have this instantaneous rise in pressure and a linear decay back to zero. There is a slight time difference here between these two elements, though. And then finally, it takes some time for the wave load to reach the rear wall, where we see that linear rise to the max peak pressure, and then we're going to see that linear decay back to zero. So let's just summarize a few of those assumptions again for this analysis. Remember, we're using this equivalent triangular loading function, much more simplified. There are more exact loading functions out there. For example, the Friedlander equation, if we wanted to more accurately represent that blast wave shape. Also, the negative phase of the shock was neglected for this example, and also some of those other variables that we listed. So dynamic pressures with drag forces, large openings, these are not included in this example. Also, the full reflected pressure was applied to the entire front face of that front wall. Realistically, if we take a look at the entire width of that front wall, we likely can reduce the pressures and the loads at the edges of the wall itself if that explosion is happening more towards the center. And obviously this would be more of an impact with the wider that our structure length is. The full side-on pressures were applied to the non-reflected surfaces. So we're talking about the sidewalls and the roof here. Remember, I use the same scale distance as I did at the front of the structure, but in reality, we could probably either use the center line of those sidewalls and roof, or we could look at reducing the loads as we move further to the rear of the structure. Now, there are more advanced load averaging techniques given to us in UFC 3-340 that you can refer to. Okay, so we are going to turn now to RFEM directly. And I will go ahead and launch the program here. So you'll notice for the sake of time, I have already modeled our structure from Design Guide in the example given. So we'll do a quick model review. There were some assumptions made, for example, with the cross sections. So we have W14 by 193 defined for our columns, A992 material. Our girders are defined as 18 by 130. We do have our purlins here, channel sections, 10 by 25, A36 material, and then we have our girts, which are 10 by 30, also A36. Now, because we have braced frames in our short direction, I did add in here some X bracing. And these are just going to be round circular sections, such as a rod, for example. But you'll notice that the member type here is unique. All the rest of our members in this example are set to a standard beam. This is anything that's a standard beam, a standard column. But for my X braces, I have set this to a tension-only member. This means that it should only take tension forces. If compression is introduced into this member, it is deactivated within the static analysis. And if tension is reintroduced, it will be reactivated due to the nonlinear capabilities within RFEM. So just something to keep in mind there. Now, as far as our surfaces, all the surfaces are defined here. So we'll take a quick look at the front surface, for example. All have the material A653 applied to them and a set thickness. Now, this thickness is a bit unique as well. So if we take a look at the thickness type, normally we would set this to a uniform thickness, which is just any type of standard surface. But I did set this to an orthotropic stiffness instead. And with this orthotropic entry, we now get this second tab here where I can directly select something like a trapezoidal sheet. And I can input in the sheet thickness, some of the geometric properties like the total profile height, the rib spacing, and so on. And the program is going to take all of this information for me and directly calculate the stiffness matrix based on this orthotropic stiffness properties. So this is all done automatically, and you have a nice view here of the stiffness matrix directly. Okay, so the final thing just to note is, of course, the dimensions. We talked about 50 feet in the short direction, 70 feet in the long direction, 15 feet in height. And our blast analysis is going to be taking place about 50 feet away from the front face of this wall here. Now, we also want to cover our loading. So I will launch our load cases and combinations dialog box. And under the base data, I have set here the AISC E7, the latest 2022 standard. Now, this really doesn't play too much of an impact in our example today because I'm not generating my load combinations automatically. You can see this is turned off here. Now, under the second tab, these are the various load cases that I've defined. And we start first with our dead load case. So we have self-weight activated within this load case. And I did assign the action category here based on the AISC 7 to dead load. Now, again, this isn't so important. If we were combining into the load combinations automatically, the program would need to know this in order to know what load factors are defined. But just for a nice categorization, we'll go ahead and apply this to the correct action category. I have 3 additional load cases here, including the front wall and the sidewall and roof, as well as the rear wall. So this is going to represent these loads from the blast being applied to the structure. The action category here is set to the load arising from extraordinary event. So now that we have our load cases defined, we need to actually apply the loads to the structure. And we begin with first our dead load. So remember, self-weight is considered here, but also I have applied an additional member load to my main girders up at the top of 0.1 kips per foot, just to account for any additional dead load within the structure. I then have that first load case here for my front wall. So you can see that this is a uniform load applied to this front face of this surface. Now, this load is a bit special in the sense that I did take advantage here of our load wizards over in the navigator, where I can apply these as member loads by specifying an area load. So if I double click on this load, we go into the load wizard dialog box. I have applied the load in the global Y direction towards that front face of that structure, and I gave it a load magnitude of 1 psi. This is just a simple unit load. So we're going to later on define the time diagram where this load is going to vary in magnitude. So we don't want to do it here with this applied load. This is why it's just a simple 1 psi. Now, if any of your units are incorrect, you can always access down here the units and decimal places and make adjustments to that. So we also have the ability here to select the 4 points for this area load, and we can also neglect members. So for example, I didn't want to consider the load being applied to my girts. So once this is done, you'll see we get a nice view here of the tributary area of the members that this load will be applied to. And we can take this a step further by right-clicking and displaying separately to see the load actually applied to the structure itself and the particular members that I have selected. So we can right-click to turn this back to a uniform load display, and we can take a look at our second load case for the blast load. Very similar concept here, but this time it's applied as the sidewalls and the roof. We can right-click here to display separately, and again, we see those loads distributed here to the main members, neglecting again the girts and the purlins. And finally, we have our last load case here for our rear wall, so same concept there. So now that we have these loads defined on the structure, we're ready to move forward with our dynamic analysis. And for this, we need to activate our base data dialog box. So this can be found by right-clicking on the model name here in our navigator, or it can be accessed through our quick tools up here in the top. This is essentially the dialog box that will pop up when we create a new RFEM model. And under this second tab, you'll see here, these are the various add-ons that we can go ahead and activate within our RFEM model itself. For today, I am going to move forward with both the modal analysis and the time history analysis. So when we activate those add-ons and come back into RFEM, you can see that really doesn't look too much different. So what we want to do is to go into the load cases and combinations dialog box, and I'm going to create a new load case here. This is going to be for my modal analysis. Now the analysis type here is going to be toggled down to modal analysis. This is available to me because I've activated that particular add-on. We then want to adjust the modal analysis settings. So for this, I'm going to calculate a total of 40 eigenmodes. I want to make sure that I get enough mass participation, that I kind of understand what's going on with our structure. We'll go ahead and leave this as the Langkos solver. I'm going to modify the mass matrix to diagonal. Now, remember that this load, this blast load, is traveling from the front of our structure to the rear of the structure in the global Y axis. And we can't see that because of this dialog box, but that's kind of what's happening there for the overall analysis. So therefore, just for a quick calculation and to really hone in on what's going on in the Y translation direction only, I'm going to deactivate the additional degrees of freedom here for my mass matrix. Now, for any further information on the different mass matrix types, solver types, you can always click on this info button in the lower left-hand corner of these dialog boxes. This will take you directly to our online manual and this particular dialog box to explain these options further. Now, the additional settings here can all be left as default, so I can click OK. We are going to import in the masses from our dead load case. We also have the ability, if we wanted to create a mass combination, we could do so. And essentially, we'll get a pretty quick analysis here. Again, the program is going to determine those 40 different eigenmodes, and we are presented with our analysis results. So you see here that we have our modal analysis results presented to us in table format, and we now have a new tab over here in our navigator with the results shown as well. Because these loads are being applied to the members themselves, I'm not so interested in kind of what's going on here with the surfaces. So I can always deactivate the surfaces from the display of my results by toggling this to none. And taking a look at the members themselves, and in particular, the second tab within the table, We want to determine here what are our dominant mode shapes. So remember, we're only looking in the Y direction. And as I scroll down through this table, I see mode number 9. This certainly has the most mass participation, so this will be one of our dominant modes. And I want to note here that the natural frequency is updated over on the left. So we'd want to write this number down, 8.832 hertz, because we're going to utilize this later on for damping purposes. And then we continue scrolling down to maybe find our second dominant mode, and that's going to be mode shape number 27. And we have a frequency here of 15.963. So we'll go ahead and write that one down as well. So now that we have this information, again, it will make a little bit more sense as we move forward. And you can also view here under the first tab, if you're interested in viewing mode shape number 9, we can see the angular frequency, again, that same natural frequency, natural periods. And we probably also are interested in mode shape number 27. So just keep those natural frequencies in mind. We'll return back to them when it comes to inputting in the damping for the time history analysis. So now that we have completed a quick modal analysis, let us move on to the time history. And in our navigator over on the left, we have a new folder here that you will see called dynamic loads. And this is because I've activated that time history analysis add-on where I can directly define my time diagram. So I double click to create my first definition here. And within my time diagram, this is where we're going to begin inputting in our information that we have determined from those slides and from Design Guide 26. So we're going to start off first by giving this a new name here, and we're going to call this one front wall. Now, as far as our time diagram input, we have two options. We can set this to user defined, which we can just input in the table values directly. And that's certainly what we'll be using today. Now, alternatively, if you had a function, so we talked a little bit about that Friedlander equation to maybe represent that idealized pressure curve in a little bit more detail, you can input in something like that function directly in RFEM as well. So for our front wall and taking advantage of the user defined option here, let us go back to the PowerPoint because I want to focus on this time diagram for the front wall only. And if you remember, we have already determined all of these points from our previous calculations. We have our instantaneous rise in pressure to 79.5 psi, and then this linear decay back to 0. We have already determined what these time values are at each of these points. So these are going to be the points that we directly input into RFEM for our first time diagram. So we go back to the program here, and our first point is going to be at time 0 with a multiplier of 0. So remember, we're going to apply this time diagram to that unit load back in that particular load case that I showed you earlier to tell the program how to vary the load magnitude over a set time. So therefore, our second point is going to be 0.01559. The multiplier is still set to 0. But now finally, under the third input option here, we type in a time of 0.0156 with a multiplier of 79.5. And finally, our fourth point will be 0.02179 with a value of 0. So you can see that our time diagram shown here in RFEM exactly replicates what we just saw in the PowerPoint example. Now you'll notice I don't have the ability here to set the same time for step 2 and step 3 here to 0.0156. The program will give you an error. So I had to offset this instantaneous rise in pressure just slightly with the multiplier of 0. So now that we have this first time diagram defined, I'm actually going to make a copy of it. And this is going to be for my sidewall and my roof. So we go back to the PowerPoint here just to take a quick overview of my sidewall and roof time diagram that again, we've calculated within our PowerPoint. So exact same shape from our front wall. with this instantaneous rise in pressure, but the peak pressure here is significantly lower because it's not oriented directly towards the blast itself. And then we have a linear decay back to 0. We know all of these times as we have solved for them. So again, this is the information we want to put directly in RFEM for our second time diagram. So the first 3 time inputs are actually all the same, but we do want to modify our multiplier here, which again is going to be that peak side-on pressure, to 24.9 psi. And then our linear decay back to 0 is also slightly adjusted from our front wall, and this will be 0.02331. So with the program plotting these various points, we now see our time diagram that reflects our PowerPoint slide that we were just taking a look at. So we then have our final time diagram. And for this one, I'm going to create a new definition here, and this will be for the rear wall. And we'll go back to our PowerPoint for the final time here to take a look at the time diagram we have determined for the rear wall. Now remember, this one looks a little bit different because it does take some time for that blast wave to reach the structure, but we have a linear rise here to that peak pressure, and then we'll see it decay linearly back to 0. Again, we know all of these points here, so this is directly what we will input in for our third time diagram. The time 0 with a magnifier or multiplier of 0, and then our second point will be 0.066. The multiplier here will also be 0. Our third point will be 0.0779. and a multiplier of 4.6. And our final point is going to be 0.097 with a multiplier of 0. So therefore, we see that relevant time diagram shown here that replicates what we just saw in the PowerPoint. Okay, so now that we have created these time diagrams, we need to actually correlate them with those unit loads that we had applied to our structure under the load cases. So we'll go ahead and click OK through this dialog box, and we're going to go into our load cases and combinations. Now, I certainly could run a time history analysis for these individual load cases, as you see here within our dropdown, but that's not the intent of this example. The structure is not going to experience the front wall blast initially, and then the side wall and roof separate from the front wall and rear wall. All of this is happening at one time, but the magnitudes are going to vary over that time duration. And the only way to combine all of these into a single time history analysis is under our load combinations tab. So we create a new load combination definition here, and the analysis type is going to be set to time diagram. Well, now we have our time history analysis settings that we'll want to go through in a little bit more detail here. So within the dropdown, you'll see that we have 2 linear solvers, including the linear modal, which is going to be a decoupled system that's based on the model's eigenvalues and mode shapes. So a modal analysis with this solver is incredibly important. We want to make sure that we do have an accurate modal analysis. Now, for our example today, we are going to utilize the linear implicit Newmark solver instead. So this is a direct time integration method. It does require sufficiently small time steps, but a big difference here is that we don't need that modal analysis whatsoever. So the modal analysis that we carried out earlier in this example technically isn't needed. I am going to use it for damping purposes, which will again make more sense in just a few minutes, but the modal analysis is not necessarily needed for this solver. So with both of these linear solvers, keep in mind that any non-linearities are automatically going to be converted to linear elements underneath the hood for this dynamic analysis. So if we had a nodal support that fails in uplift, but in downward compression fully re-engages, underneath the hood for the dynamic analysis, it will be just converted to a linear nodal support. For our example today, we have a tension-only member. Well, for a linear solver underneath the hood, it's converted to a truss element. So it will take both tension and compression forces, and this is just simply a limitation of these linear solvers. So moving forward with the linear implicit newmark, we do need to set our max time value to run this time history analysis. And for this, I'm going to set it to 0.5 seconds. These blast loads are incredibly quick. There's really no reason to run a 26-second time history analysis. That's far too long, but we can more or less understand the structure's response with something like a much shorter time duration. Now we have two additional inputs here, the save time step and the split save time steps. So the difference here, the save time steps, this is what the program will output in our results once we run the calculation. So it's important that we kind of set this to something that's small enough that we understand and get an accurate representation that's output in RFEM itself once that calculation is done. Now, if we wanted to use additional time steps for the solver itself, we can further split the save time steps. But what's nice is that we're not going to export every single time step out, which is really going to bog down our results and viewing within RFEM. So that's kind of the difference between these two. Now, for our example today, I'm not going to split the save time steps any further. We'll just go ahead and use the same time steps, save time steps of 0.001. With all of that said, the time steps, again, this is really important for the linear implicit newmark solver that you carry out a time step study. And what I mean by this is go ahead and set your time step. Take a look at your results. Come back in, reduce your time step even further. Do your results change significantly? If they do, then you need to continue reducing these time steps so that eventually we see the same result output between the time steps themselves. And this is really a balance that we don't want to be reducing the time steps so small that the calculation is taking too long. But if you set it to something too large, then you're not going to get accurate results. So again, carrying out that time step study will be very beneficial. The calculation parameters, I will modify here the mass matrix to a diagonal, maybe not too much difference between the consistent versus the diagonal here. I'm going to go ahead and uncheck the degrees of freedom for rotation about my global axes, but I will leave translation activated for this mass matrix. And finally, we have our damping. So when we talk about the newmark solver and damping, we always refer to the Rayleigh damping parameters, alpha and beta, where alpha is going to be the mass portion of that stiffness matrix, and then we have beta, which is going to be the stiffness portion of that mass matrix. So we want to ensure that these parameters are input in correctly. Now, most of us might be used to Lear's damping, where we just have a set percentage to input for the damping itself. And we have a nice tool here where we can actually convert from Lear's damping to Rayleigh damping by inputting in the natural frequencies of our two most dominant mode shapes. So that should ring a bell. This is why we carried out that modal analysis to determine what the two dominant mode shapes are. Remember, we wrote down the relevant frequencies from mode shape number 9 as 8.832 hertz, and then our frequency from our second dominant mode shape from mode number 27 is going to be 15.963. Now, the Lear's damping is 2% for this structure. So I can input in this information directly, and you'll notice alpha and beta are directly calculated for me. So nice feature directly for the damping considerations. So once all of this information is input, we're going to import the masses from the dead load case once again. But under the assignment, this is where we want to move our 3 different load cases over to the right-hand side by double-clicking on them and relate them to the relevant time diagrams. So we have our front wall, which is going to be related to time diagram number 1, our sidewalls and roof, which is going to be related to time diagram number 2 for the sidewall and roof. And finally, we have the rear wall, which will be related here to time diagram number 3. So I'm going to begin this calculation here. And for this linear solver and the time steps that I have set, we will see this solve pretty quickly. So what's happening here in the background then? We're now going to apply each one of those unit loads. So we had, remember, the area load at the front face, the sidewalls, the roof, and the rear wall of the structure. But now we're going to apply those 3 separate time diagrams to tell the program how the load magnitude of this blast wave should vary over the total time duration of 0.5 seconds. So ultimately, once this calculation is done, we will see our results here within the navigator over on the left, but also I'll go ahead and activate my surfaces within table format. And as we take a look at the save time steps here within our dropdown, we cycle through these and we see, not much is happening. But remember, it's going to take a small time period before this blast wave actually reaches this structure. And that happens at 0.016 seconds. And then this is where we start to see deformations on the structure. So we can cycle through these time steps to see the deformation graphically change here as that wave load moves from the front of the structure to the rear of the structure. Now, the time history analysis results are also available here in table format. So for example, if we're interested in the internal forces of our members as an envelope solution for this time history analysis, we can export this information to Microsoft Excel with the click of a button for further sorting. So this could certainly be beneficial to review as well. One other nice feature that you may not be aware of is up here in our tools, we have what's called the calculation diagram monitor. So I can activate this and you'll notice it populates down here and maybe I temporarily close out my table. This has a drop down here that includes all of the result information from this time history analysis. So if I want to take a look at my acceleration of a particular nodal point, I select that here. I could graphically select maybe a node at the front of the structure. And maybe I'm interested in the accelerations in the Y direction. So we see that plotted here within the diagram monitor over the 0.5 second duration. We could also toggle this here to maybe the global deformation of that same node. And maybe I'm interested in the global Y deformation only. So again, we can see that plotted out here as that wave load moves from front to the back of the structure. We can also right click under the time steps here to start this animation. So you'll notice that the program is kind of moving through step by step here. The deformations are changing graphically to show you in more detail what's going on. The final thing that we'll touch on is under the navigator for this linear analysis is the calculation diagrams. So this is actually very similar to the calculation diagram monitor. The benefit of this though is that we can create as many calculation diagrams as we want and this will actually be saved to the model. So we can begin with first a time history analysis with our analysis type. The program says, oh, okay, I need to toggle this to my load combination then, because that's the only time history analysis I carried out. We have our time on the x-axis here, and on the y-axis, we have that exact same information that we previously saw with our diagram monitor. Perhaps we want to take a look at the member internal forces, and I'm going to select here the axial forces, and I'm going to graphically select my tension only member. So member number 74. I also need to choose a node along that member in order to plot out the internal forces at that particular location. And what you'll notice is that this tension only member certainly has tension forces in the positive region of this diagram, but because we're utilizing that linear solver, it is converted to a truss element underneath the hood for this dynamic analysis. So now we're seeing a lot of compression forces within this member as well. So we'll kind of wrap up here the linear analysis. Now, because we have these nonlinear elements, maybe we want to turn now to a nonlinear time history analysis. So I'll go ahead and click OK in this diagram, and we will revisit here our load combinations dialog box. And this is quite easy as I'm going to make an exact copy of my existing load combination number 1. You can see it copied here, but I'm going to go into the time history analysis settings and I'm going to make a copy of my existing settings. And I'm going to select here the nonlinear implicit Newmark solver. So as mentioned, this was released relatively just a few months ago, and this is a phased release. So not all nonlinearities are accounted for right now. So for example, we put a lot of effort and testing into member nonlinearities, nonlinear nodal supports, nonlinear member end hinges, but something like a nonlinear material is not quite ready. The program will give you a warning if there's something that's maybe not supported yet or untested, just so that you're very aware of what's available with this particular solver. But with our tension only member today, this should certainly be considered with the nonlinear implicit Newmark solver. Now, it's important that we decrease our time steps even further. So I'm going to add an extra 0 here for my save time step, 0.0001. I'm not going to split the save time steps any further for this particular nonlinear calculation. Again, we'd probably want to carry out a time step study. For the damping, it is important to know that in the current state for this nonlinear Newmark solver that we cannot consider the beta damping parameter. So it would be best to actually set this to 0. Now alpha is still considered, and we will continue to improve on that in the future as well. But we do need to get convergence for this calculation, and we can only do so by setting beta equal to 0. So once this information is set, we're really ready to run the calculation by selecting these new analysis settings here that we just defined for the second load combination. Everything else is the same under the assignment tab. Again, those load cases are associated with the relevant time diagrams. Now, I have an already saved model here that I'll go ahead and open up because the calculation does take a few minutes longer for that nonlinear analysis. Everything that we saw for the linear analysis is still relevant. We can take a look at the various saved time steps here, the global deformations, this calculation diagram monitor. Again, everything is still equivalent for the nonlinear calculation. The difference here, though, is that let us revisit our calculation diagram. So if we go into that calculation diagram, remember, this is exactly what we just saw for our linear time history analysis. Well, I made a copy of this one by using the copy tool down in the lower left to select here my nonlinear time history analysis, that load combination number 2 here. And we can see that it's a pretty big difference. We are now able to account that this is a nonlinear tension only member. Therefore, we should see only tension forces in the positive area of this diagram. The minute that it sees compression, it's completely deactivated from the calculation. So certainly a significant difference here if we are wanting to consider those nonlinearities. If I do zoom in here, it's also important for these nonlinear calculations that we get these more or less smooth curves here. If you're seeing very jagged results in this diagram, that probably means that you need to decrease your save time steps and possibly even your time steps for your calculation further. Okay, so that will wrap up our full example today, going through both the linear time history analysis as well as the nonlinear. We'll go back to the PowerPoint here to wrap up today's presentation. If you did like what you saw with the time history analysis and are interested in RFEM for these capabilities or any other capability that we offer, we would love it if you reached out to our sales team. You can do so by scanning this QR code, visiting our website, or our contact information for our Philadelphia office, including our phone number and our email are shown here at the bottom of this screen. We can certainly get you set up with the 90-day trial version, send you some learning resources. So again, if you're interested, please reach out here. We will have many more upcoming webinars. I tend to do these about once per month. You can register at dluwell.com under support and training webinars. As most of you know, I usually send out a reminder email about a week before these take place. So keep an eye out for the next one and you can register directly through the email itself. Now, PDH certificates will automatically be emailed to all participants. This is not instantaneous when the presentation ends, but rather these will be sent out in the next 1 to 2 days. Now, if you were here for the full presentation, you can certainly expect that PDH. That is a requirement of the states that we are pre-approved providers, that you're here for the full 60-minute duration in order to receive that. If you watched with a colleague or you watched in a conference type setting and you yourself did not register for this GoToWebinar, you will need to request your PDH to our email address shown here, info-us@delubal.com. Let us know who you watched it with, and we will certainly send you a PDH certificate. And with that said, I want to thank everyone for attending our webinar today. There will be a short survey that pops up when you do exit out of the GoToWebinar. And as always, we hope to see you at our next presentation. Thank you.